So welcome everybody to this second session of Python. So after the introduction, well, the two different talks that Olivier gave today in the morning, now in the afternoon we are going to have a look at this presentation titled "How to make an efficient use of Python on the clusters." And what do we need of trying to do and making an efficient use? So as Olivier already presented, Python is a highly abstract language, dynamically typed. Let's say the principal objects that are used in Python, if we just rely with pure Python, the objects like lists, dict, even if they are super flexible, they are far from ideal for writing a code which is meant to have a huge amount of to involve a huge amount of computations. So it's not ideal to represent vectors with Python lists, for instance, and doing linear algebra between Python lists. So that's the reason he already mentioned, and well, most of you must be aware with the Python extensions like Numpy, scipy, pandas, and well, scikit. So those are developed in principle to provide a Python a view inside precompiled binary libraries, which are basically written in C or Fortran. They are compiled, and then we have an interface which allows us to call this library from Python code. So mainly, so this presentation is divided into main parts. The second part will be a little bit talking about what's behind Numpy, scipy, and have a look at how we can create our own compile libraries in case we need to implement some kind of algorithms that are not available on the extensions provided. And on the first part, we are going to see which kind of tools we have available in Python for doing code profiling. So code profiling means optimizing code and optimizing it by using tools that allows us to analyze how much time I spent on different functions in my code, and then I can then focus after I detect where I have my bottlenecks on the code. Then I can focus on that and those most time-consuming functions to try to think how we can rewrite them, how can we make them more efficient. Eventually, we can if we are starting with a function written mainly in pure Python, we can think about porting that to a binary library. So we are going to take a look at a couple of tools for doing CPU profiling and memory profiling of Python code. In order to do that, we are going to have a kind of example problem, kind of toy code in which we will implement this algorithm, the sieve of Eratosthenes. So it's an ancient algorithm to find all the prime numbers. If I have a list of integers up to a given limit, the algorithm allows me to filter out which are the primes on this list and how it works. So here it's explained which are the steps. So I have to start with a given list. So from 1 to the limit, we know that 1 and by definition 2 is already the first prime number, so we take out already 1 from the list. And then the algorithm consists on taking the first element of the list and then I will move through the list in displacement multiples of this element. So the first one here is 2. And then I do displacements multiples of 2, and then I cross out all of them, because then by doing that, I'm jumping onto all the multiples of 2. So I know 2 is the first prime, and then every displacement on 2 I cross out, I remove it from the list, because those are multiples of 2, so no primes. What I do in the next step, I move to the next element that's still not crossed out. In this case, it's 3, and then I move on multiples of 3, and I cross out the elements that have not been crossed out before, or up to the limit. Then so I move again to the next number non-crossed. I move it in displacements multiples of 5, and I cross out them, and so on. So by doing this procedure, at the end, we end up with the non-cross-out number 2, 3, 5, 7, 11 are the prime numbers up to that given limit. We can see already that actually, there's a trivial optimization that we can do, that after I move to a given step, actually it's not necessary that I check all the displacement, for instance here multiples of 5, like 10, 15, 20, they've been crossed out before, because actually they were multiples of this and the previous primes on my list. So I can actually jump directly to n squared, so to 25. You see, it's the first one that I have to still available to cross out, and then move from n squared up to the end. So you see again also when we did this step, I put up directly to 9. It's the first non-cross. So 6 was already crossed because it's a multiple of 3 and 2. So we are going to do a very basic, to start with a very basic, simple implementation in pure Python of this algorithm, and it will allow us to explore a little bit the profiling tools we have. So here, yeah, as I said, this is a pure Python implementation of it. So we start up. I have my code, which is calling just this function. It's the only one that I have, and the function primes up to a given limit. If I call it with a number, it returns me a list with all the primes up to that limit. And well, as you see, the function is it's creating at the very beginning a list, a Python list of booleans. So true and false. Every element in the list will be a boolean, so with value 0, 1, true or false. So we already, so the first index of the list is 0. So 0 and 1 we are declaring them as false already, and then we have a true up to limit -1. In order to have each index representing the natural number, and if it's true, then at the end of the algorithm, if that the value I have for that index is true, then it means that the value of that index is a prime number. So we start with the list, we create the list, and then we do the loop. As I mentioned, we go up to the square root, and each time that I enter on the list, I do. So I move from I to the limit, where I is already n squared, and then I start doing the displacement with multiples of n, and then crossing out means declaring each of them as false. So here, this is the part in which I'm doing the displacement and the cross out. And then at the end of doing that loop, so the for loop and the eternal while for each n that I'm jumping. Here we have a list. So we return the list of prime numbers. We build that with a list comprehension that you saw. Yeah. So we create a list to be returned with this list comprehension statement, well, in which well, we move through all the I that are true. We are building the list, yeah, with the value of the index for which is true the value. And so, well, if we run this thing that we see here in the screen and we execute it with well, asking up to 25, we get this result, which is kind of what we saw in the explanation of the algorithm. And so if we, yeah, of course, we are here running this up to 25, it will take almost nothing to run it on any kind of computer. So if we remove the print statement, otherwise we will get a lot of a huge amount of things written in string. But so we remove the print statement, but we ask all the primes up to 30 million. Roughly that in a typical CPU, well, this is a bit oldish, but in a CPU of most common laptops, it will take about 10 seconds to compute to do all this computation up to 30 million. And so this is what we would get if, yeah, to the code I showed before, if we ask up to 30 million. And so the first tool for doing CPU profiling I'm presenting here is the one called cProfile. This module is part of the native Python library. So any Python installation will already contain it. This is part of its standard library. So I don't have to pip install it or pull it from somewhere else. It's part of the core Python package. And this tool, it will well, hook into the Python virtual machine and then look during the execution of the code. It will take a look at how much time it was spent on each different function that was seen by the Python virtual machine. And then if I execute it with this, so I load the cProfile module and I use this cumulative option, I will get printed on screen information, this kind of information in which I see, yeah, here the main thing is the last column is the different functions that are seen by the Python virtual machine, and then how much the total time of the full runtime it spent on that function. So we see here that from the 10 seconds, or almost 11, 9.5 were spent in the primes up to function. It's the only function of that we wrote. Then the other significant part is in the list comprehension. So that's creating the reduced list to be returned to the main. And yeah, so well, we have a small example here with a single function, but it's well, still useful to present the tool. But of course, if I have a big code with many different functions being called and so on, I will it will be hard to read or to capture it will be hard to analyze just from seeing all this in text if I have like 100 functions. So there are visualizations tools which will somehow represent this they will produce a plot to show the relation between the functions and how and how much time is spent of each of them. Well, one popular one is called this one called snakevis. This one is not part of the Python library, so it has to be installed for either pip install or it's available in many Linux distros as a package. And this tool, if I, so I will then show on my, I will, my, I will show here running on my laptop what kind of thing we will see. I will point you then in a slide later where you will find on the SESI cluster, you can find a folder with all the examples that we will show. So if you want then to test this thing, you don't have to copy paste. So yeah. So here I have this code as we saw on the first slide. It's just what we saw on the first slide, evaluated up to 30 million. And so if I run this, here it will be slightly less than 10 seconds. So yeah, about 7 seconds. And I wanted to copy more. So we run we load the C profile module, but we use this other option instead of the S cumulative, and this will dump a binary file, which has all the profiling information. So this is a binary file, and you need then a tool which will understand the information there. And so the tool will start a small web server, and it will pop up a browser. It will pop up your default browser. Here I got it in the second screen, showing you that page. It creates I don't know why I lose cursor. But okay, so well, normally if you do it on your computer, you will be able to move around with the mouse and even to click on those different boxes. But the big overview that you see is so it will show you, it will represent you the so here below we have what we saw on the what is dumped on the screen with when you run it with the cumulative option. So it will represent each of these functions. So you will get on top the main part of the code, and then below every other function that is being executed. And if that function is calling another, you will get it below the box. And then the length of each box will be proportional to how much time was spent on running it. So here, as it's just a code with a single function, we get everything called price up to and price up to, which is where we are spending most of the time. But if we imagine that from the main we call price up to and then some other one and so on, then you will get different boxes, each one representing how much time was spent on each of those. So then, yeah, if you have your own codes, which for sure we will be using more than just calling a single function, doing everything, you will get some nice graphical representation of the time being spent on all your different functions. And then, yeah, so here, using the cProfile module, then we get information of how much, a global view of all my code, and how much time was spent on every different function that was executed during my code. But then if we have a code with many functions and we want to focus on one, if we detect, for instance, with this first run, kprand sub2 is where we spend most of the time, and then we want to focus on that one, we have this other tool. This one is not part of the standard library, the line profiler module. So this one must be either pip install or pulled from the repos of your distro, if you're in Linux. And then, yeah, if you have this available on your Python environment, then you can use it to do a line by line to obtain information on inside a function of how much time was spent on each line of your function. Given this, this kind of profiling it does, it will introduce then a big overhead on the execution. So it will be way much slower than just running it without doing this analysis. But yeah, the way it works is by adding the way I use the tool is by adding this add profile decorator on top of the function that I want to obtain the profiling information for. And then the module provides a binary, a kernprof tool that will do the actual profiling. So if I have the code I just saw, the only thing that we modify is adding the add profile on top of primes up2. Then we use the kernprof tool provided by the extension with these options, and we will get then this kind of information. Yeah, you see that the total time of running this, instead of the 10 seconds, it was about 100 seconds. We are 10 times more. Our runtime it was increased by a factor of 10. So yeah, this is to know that we will use this tool very specifically on given functions, because if our code runs in 10 minutes, then it will be 100 minutes. But the idea is that we get much more information of what's going on inside a given part that we detect that we are spending a lot of time. In this case, so then the information that we get here we actually get in the last line the code, the source code of the function that I added the profile decorator. Well, here is the line number, and here we are having information of the number of hits, the number of times that the Python virtual machine spent, but the number of times that each of these sentence was executed by the Python virtual machine. So we see that then the biggest number of hits is on this part, on this in the most internal loop is where the loop that is being executed for each n, and then doing all the displacements on number of n up to the limit for each n. So it's quite true. It was expectable that we were going to spend here most of the time. But so here we see the way it's shown the information here is how many times each of these line was executed, and then here on this column we get the percentage of time that represents for the, if we add up here, this will be 100%, and it's just the time spent on executing this function. If my code has many others, but I just put the add profile decorator to a single one, this will add up 100. It won't count the time spent outside the function that I'm profiling. So this means that on these 3 lines, I spend 90% of the time on executing this function. So I spend the 9 seconds of my 10 seconds when we run it without the profiling. So well, then this is in order to go after I detect a given function consuming most of the time, then this can allow me to go and look inside what's going on. Of course, I can have a much more complex function doing different things, and then I can focus on the statements that are being the ones where I'm spending most of the time. So the idea, we have this kind of toy problem that we can already infer by looking at the code where we are going to have most of the time. But it allows us to, it allows me to present you the tool and go through. But and well, so then the idea is that this points you to where you have to focus on rework your code, or adapt or change it, or look for if there is an extension for doing the operations that you are doing on that part. And after that, we are jumping to another tool which will analyze the memory used during my code execution. So it's called memory profiler. The idea is to get information of how it's been used, the RAM memory by your code. Or it works also on a kind of a line-by-line approach. So the way of using it is similar to the line profiler. I need to tag a given function to tell the tool to focus on into that function. And then so I execute. It's not part of the standard library, so we have to pip install it or pull it from a repo. The way in which I use it is by just loading the memory profiler module on the execution of the code, and then I get the information I will get with this approach is which are the memory deltas that I have as which are the memory deltas that I'm having for each sentence, for each statement being executed. So we see that we actually have so we entered already with a delta of 30 megabytes to the function. Then when I enter the function, I have a delta of 230 megabytes almost after executing this statement in which I create my list of 30 million elements. And actually, after I created that, I don't have any more deltas, because actually what I'm doing afterwards is just moving through that list and crossing out. But I'm not allocating any more objects in memory. But so well, this is the kind of information that we'll provide. I must remark that this memory profile it needs to hook to the Python virtual machine and monitor each statement executed in the full runtime of the code. It will introduce an even bigger overhead than the line-by-line CPU profiler. But well, if I want to focus, I'm noticing that my code is eating big amounts of memory. I can suspect where I have memory allocations of my code, and then tag the specific functions where that's happening and see what can I do. The important thing is that to remember that each function that we tag, it will increase like factor of 50 here, not only 10, the runtime roughly. But the thing is that this, what is interesting with this module is that it provides me another tool. What we will see just after this slide, which is, it doesn't introduce a big overhead, and it's really useful to analyze both the memory usage and the CPU usage. So if we want to, now we saw that here that we had the delta jump of 230 megabytes after the creation of my list of 30 million elements. So we can try to analyze why is this amount of memory allocated on that line. And then if we read the Python documentation, we will see that for a list, every element on the list that it's a Boolean, it will take by default 8 bytes. So it's a standard for a long int in C. So it's actually a bit excessive, but yes, given this dynamically type approach that Python has for its variables, it will by default, even if it's a Boolean, eat 8 bytes for each Boolean. And then we see that, so we are creating in memory 30 million elements of 8 bytes each. If we do the math, we will get exactly almost that amount of memory. So we have 30 million elements of 8 bytes each, and then we divide to go to kilo and to mega, and we get the 228 megabytes. So here is just the remark that I mentioned before. Running this tool, it gives it makes the runtime even slower. So then actually you will either run it for a specific function or run it for a reduced if it's possible and meaningful, you will reduce your problem when you are doing profiling, so you can focus on the parts of the code that are consuming time, but with a small problem, so you don't have to wait a lot for even the overhead that is introduced on it. But yeah, the thing is that also just using the tool in this way, we can actually, as we will see right now, that we can actually even not capture everything that's going on with the memory allocations of your code. And yeah, the memory profiler tool provides this provides this mprof tool, which will allow me to obtain some kind of graphical representation of the memory bit. It will give me a plot of the memory used as a function of time of my code. And yeah, how do we run? So how does it look like to run it for our toy problem here? So the 601 up to 30 million, we run it. So we use the mprof tool to generate the information for the plot with this command. And after that, it will actually, it will dump a plot file that, it can be rendered. It will dump the information on a file on the same folder where I have my code. And then if I type mprof plot, it will read the last plot file created in that directory, and it will directly show it by using a mathplotlib. So you need actually mathplotlib is a dependency for the memory profiler tool. When you do pip install, it will pull mathplotlib also if it's not already installed. And as I said, the information that it will give me, you see that it has a little overhead, but we stay on the same order of magnitude. So we spend about 11 seconds to run my code, and then it shows me as a function of time how much memory I'm using, and we see that we actually have this on the information before. We saw that after entering my function, we ended with we had this jump of 230 megabytes, and then the code stayed there were no more memory deltas after that. So we had this jump of 230, and then we stay roughly on that value. But we see here when by doing this plot that we actually have some peak almost at about 500 megabytes before even being in this 230, 250 megabytes of memory use. So we got this peak, and then we stay about the 250. So we will try to we will see now how can we get more information about what's going on that peak. In principle, here we just run this without touching at we didn't add any decorator, any nothing. It is the original code from the first slide. But we can the module provides some methods for adding more information on the plot. So we can group, so inside of this statement of this with profile.timesTime statement, we can group a parts of the code, and then I will get extra information on my plot of actually, but it will show me how if I add this profile.time create sieve, and here I have just the statement creating the sieve list, and then we run again the tool. It will on the plot. It will add this. It will add this kind of brackets with different colors for each code that is part that it's inside of a timestamp section. So we added this for the create. So we added 2 timestamp create sieve list, which is just the creation of the 30 million elements list, and then another group in all the part of the code where we are doing all the cross out. And so we see that the peak of almost about 500 megabytes is happening just on this line in which we are creating the list. But we have this peak, and then we go down to 250, and then on the part of the code that we are doing the cross out that we saw on the first run. On the detailed run of the delta memories, that we were not having any delta memory during the cross out, and we see it here in the plot that the memory used by the code stays without any increase during that cross out, and then we see that we have this increase of memory being used, and then it drops when it's finishing the code. So actually this part, which is not included in the cross out timestamp, is the list. So that little part, that little increase, is the least comprehension I'm having when exiting the function, which is not part of this timestamp that I put. So it's the creation of the list to return. So you see that using this tool, especially with the timestamps, it can provide information both of actually how much time if I read it here, how much time I'm spending on that section that I put the timestamp, but then I have also information of the memory being used. And so again, to the peak of 200 of almost 500 megabytes, if we experiment a little bit with the tool by expressing differently this part, the creation of my list of 30 elements, we see that it was created this way by adding. So it was created a long list by the addition of 2 different lists, a list with 2 elements and a list with the 30 million minus 2. And actually we can see, if we write this differently, we can see that doing that is actually equivalent. So Python will execute it exactly equivalent as doing all these 5 statements. So creating originally one list of 2 elements, creating a second list of the 30 million minus 2, then creating a third in which is doing the by the concatenation of the two, but it's a third independent from these two, and then it's deleting the SIP1 and the SIP2, and I just keep the long one. So actually you see that here I have a list of 30 million minus 2, and here the list of 30 million. So I have for a small during the execution of those 5 statements, I have for a small amount of time two lists of almost 30 million in memory, and that's the reason I have the double of the memory being used just for a short time. But anyway, I need that memory. If I leave my code like that, I really need 500 megabytes available on my computer to build it that way. And so if we do something, so this was done like that on purpose, not really efficient. So if we do instead the creation of a single list of 30 million at once, and then we just declare, we operate on that single list that I have in memory, and I set as false the first 2 elements, and we run. So yeah, from my code, I just change here the line that we were having the list creation by the addition of 2. We change it this way, and we run again the mprof, and we see now that we don't have at all this peak. So yeah, you see, but by doing this change, we are not, for instance, we are not. We don't need unnecessarily to have double of the memory available on the computer, because if 500 megabytes is not an issue, but depending on the size of the problem I'm studying, having 10 gigs or 20 gigs, it makes a difference. So this is a little bit to illustrate how we can make use of this tool, of the timestamp thing, and how we can use them for what they are meant to, for detect bottlenecks or peaks of memory or whatever, and see if we can do something different to change that without impacting at all how the code, the execution of my, without changing at all the algorithm behind the code. And then we still have the time spent during the cross out, and then the list comprehension, and then the code returns the list and ends. And after presenting you these tools, I don't know if everybody has already access to the clusters with the computers that you have, each of you have here. The idea is that we do kind of a small break, and you can experiment with if you have access to any of the SESI clusters, then you have this folder is available on the common storage of the SESI, so it's available for many clusters. You can you can run this to copy this folder to your home, and then there's after you copied it, there's a README file which has some instructions on. It will ask to use this. It will show you. Let's open. It will ask you to play with these tools that we just saw for. There's a code which is a pure Python implementation of the 2D diffusion equation. Also, by the way, I don't know if you go to the. I will switch to show you that you can get the slides on a browser. If you go to the Indico website where you registered for the course, and you look for the session today. So here, and I don't know why I missed the cursor on the groceries. It's maximized. So if you the sessions of today. Contribution list, and then this session in which we are now. Yeah, you will find them by going there. The PDF of the presentation I'm showing. So then you can have that open on your computer. And so then what you will after you copy the folder in the in the exercises subfolder, there's the README, and it will the README is this one, and then it tells you how to, well, you already have the presentation about how to using the module tool to load the different software that we have available on the cluster. You know that we have different versions of Python with different versions of the Python extensions, and then you can choose a specific version, the one that you wish. You might need Python 3.7 or 3.8 or 3.9, sometimes maybe depending on the code you are working on. So you have the instruction on how to load the minimum by the mathplotlib module and a Numpy module that we will see about that later. And then this was already mentioned by Olivier on the morning. You can create, so here you have the instruction to create a virtual environment on your home folder in the cluster. Then how to initiate it, how to activate it, and then you can click install stuff inside the virtual environment. So this is very nice. If you're working with Python, it's good to get used to this kind of approach to load the modules that you need, and then create your virtual environment in case you need to. You're needing to pip install extra extensions that are not provided on the modules. But remember, just as a refresh of the module tool, there's a lot. If you type module avail on a cluster, you will see a list of all the different software that it's already available as a module. there's not just what I show. You see, for instance, you have here I'm on Mid 5. There's PyTorch already available. That's a big package. There's I think there's a CPU version of TensorFlow. On Dragon 2, you have TensorFlow available for CPUs and also on Hercules. So before, when you are needing for some Python extension, always check with module avail, and you can just put a part of the name of the extension, and it will show you. If you know that you need PyTorch, you can feel, instead of just module avail, you add a part of a keyword like module avail torch, and then it just show you, it will filter out the list. So there's a lot of extension already provided. Before you go, before going the way of installing Conda, whatever, check what it's already available. And if still something missing, then you can do like the README suggest you pip install those. And so after you get the environment, the idea of the exercise is to use the very first tool that we saw, the C profile, to see which are the most time-consuming functions, and then choose the most time-consuming one and profile it with with ChemProof by adding the ChemProof from the line profiler extension to see which is the most time-consuming line of that function. So there you will have to add the decorator. And yeah, the idea is to do that for that code available there on the folder, which is just a very very basic pure Python implementation of solving the 2D diffusion equation. So it's implemented by doing finite differences of the differential equations, and then you have three. So you have the main calling to the integrate function by passing it the number of iterations, the time delta that I would use for the finite difference, and in values. So here the idea is modeling how a small how ink will diffuse in a drop of ink will diffuse on a given liquid. But yeah, it's just and so yeah. Well, there are three functions. One which is just creating the grid and setting the value. Setting the value of that amount of that represents the amount of ink on a given central part of the domain, and then the integrate so the integrate function, it will call initialize to create my, well, it will be a list of lists. As I said, it's a pure Python implementation. So the array representing all the, on a discrete approach. My domain, it will be a list of lists, and each element of the list, it will have a value of the amount of ink present on it. So after initializing, integrate will call evolve on a for loop, and evolve is going to do the final difference for each time step, and then it will do that for the number of iterations I asked. So of course, yeah, well, it's already it's still a kind of for problem. We can already infer from the code where we are going to spend most of the time. The idea is to familiarize yourself a little bit with the tools. Sorry, the ones I mentioned for the mathematics and yes. Just copy and paste one by one. Yeah, actually, it will have to complete one. You know, if you don't know your load and then you type NAT and you press start, it will complete with mathplotlib and. Yeah, yes. Yes. Okay, now it works. But why do you want Maybe because we are all testing directly on the login node, reduce this to the number of iterations to any to avoid waiting a lot for. Yeah. Yeah, do that on the main, reduce the number of iterations to 20 from 100 to. Yeah.
So what's the thing? I will do this way for you have the yes. So you want to have discussion just the two of the parties.
Yeah.
And so it has the sensitivity and then for find out.
No, first you profile the C profile that will give you the amount spent of each, and then with the line profiler, where you add the decorator.
Yeah, so that
Only on the mode, but you add that.
yeah, for instance, this is
on
the
the, yeah,
for instance, this one,
okay.
and this is the other one, and this one is the big one. So, actually, it's one,
But yeah, well, the idea, well, if you do it for the three, it's the same. Yeah, the idea is to a little bit to play with the tools. To see, yeah, it's let me check. You added the decorator on a function. No, because then it will, yeah, it will do nothing if you don't add it. So yeah, well, I will. I will put here, so I'm what, yeah, which was the idea of the exercise. So in the first point, the idea is to run, yeah, the full code by loading the C profile module. So then we get the dump of the information of how much time is spent on each of the different functions. And we see that, so for the full runtime of about 4 seconds, we spent most of the time on the evolve, which is, yeah, the one I'm calling for each time step from the integrate function. And yeah, on the integrate itself, the Python virtual machine, it spends no, then it's that one where most of the time is spent. But you can see also, yeah, here I didn't mention, you have this, which is called the cumulative time. Actually, integrate is calling evolve. So even if it's not spent a lot of time on integrate, the accumulated time, because it has to wait for evolve each time it's being called, it's bigger than evolve. But anyway, the most time consuming of my tree, the way it's written, is evolve. And then, yeah, actually, I reread that I wrote to use kern proof for each of the three functions. But yeah, but if you reduce the number of iterations to 20, then you could maybe you could have done it already for the three, but then you can just focus on evolve. But remember, for using kern proof, then you have to modify the code. In principle, just adding the add profile decorator on top of it. After you add it, then well, you can run it. So I just name it differently. The version with the add profile added. If you run kern proof, you should get something like this, where similarly to the sieve that we are having in a loop of loops, we see that the most inner part of the loops are the statements being executed most of the time, and then it's where I'm spending most of the time on the statements. Well, we do the actual finite difference for each element of the list. So the idea is to have an idea of how to prepare the environment on the cluster. That's important to get used to loading modules, creating virtual environments, and so on. You can do the same on your with whatever environment you use on your laptop. It's a good idea to have this tool actually set up on the laptop where you are developing the code, and then on the cluster you will just copy it to run actually, and not for doing the profiling there. Yeah, that's that was in the idea of this part, so we can continue. And so far, even this this code that it's there to do the exercise, we just so it's still a pure Python implementation. So we are doing linear algebra with Python lists, which as I said at the beginning, that's far from a way to do something really non-efficient, but it's not thought for that. For that reasons, we have a couple of big projects in which are meant to be used from Python for doing mainly, but Numpy, it's mainly the big amount of methods implemented on that module is for doing linear algebra, and then and many other different things built on top of that. But then, so the main thing is that an extension as Numpy, it provides a totally new kind of object of that doesn't exist on pure Python. The array object, they are called in Python they are called buffer-like objects. One of the main benefits of that, which is actually thought for doing scientific or numerical computation with them, is that then this object, they won't be dynamically typed. I will have to, when I create an array, a NumPy array, I will have to tell which size it will have and which data type all the elements of the array will have the same data type. They will be all integers or floats or complex numbers, but they will have exactly the same data type, and they will be a size defined. So they will be allocated on a contiguous part of memory, which is not the case for a Python list. They can have all the variables stored scattered in memory. So that kind of array on a contiguous block of memory with exactly the same data type from each of the variables of the array is exactly how arrays are defined in a C or Fortran code. Then if I have to do operations, especially linear algebra between them, like dot products or stuff like that, I will move in a contiguous block of memory. So it's a way more efficient way to use the hardware to move, in my code, to move on contiguous block of memory rather than accessive variables that are scattered on different parts of the memory. And then the thing is that NumPy provides me a lot of for these array objects methods to apply to them. So like a method for doing the dot product between two arrays, and then the code that it's being in charge of doing that linear algebra, that operation, are actually binary libraries which are written in C and Fortran, which are already compiled, but I have an interface to anyway access those methods or access this library from just a Python code. So I don't have to care about writing a for loop for doing the dot product between two vectors. I just use a method which is part of the of these objects, part of the NumPy extension. And that's actually then having a more efficient Python code in this sense is actually because it's not being Python, but it's a reason for which this project exists. Then they are super useful, they are super efficient, and then I have a view to work with them, which still looks like high level. So it can be compared, using it interactively. It can be compared to a mathplotlib-like functionality. And then on top we have NumPy. It's the main core of many other tools which are built on top of it. Well, then let's see what we can just now with NumPy, what kind of how can we implement the pure Python code that we had for the sieve by using NumPy. So we start in principle just with replacing my original list. So in the second implementation, in which we are creating just a single list, then declaring as false the element the Boolean in the index 0 and 1, declaring it as false to start with 2. If you compare, then the only thing we are modifying is just importing NumPy and creating my list as a NumPy array, where every object, up to 30 million, every object is up to the limit I pass to the function, and every object is of Boolean data type, and NumPy Boolean data type. Just modifying this single line. If we look at the memory and we run then that code by changing from my Python list to a numerical a NumPy array. We see now that the jump on the timestamp create the sieve list. We from the 230 megabyte we have before, now we have about a 30 megabytes jump. And then we can see that, yeah, for a NumPy array, each Boolean, it has actually, yeah, just 1 byte of, it's taking on memory just 1 byte, which is all I need for storing a Boolean. And then if we do the math of storing 30 million bytes, of memory, how much it would take, and then we get the number of this almost 30 megabytes. And then, yeah, we have roughly the same behavior. During the cross out, memory doesn't change. We still spend about 10 seconds on that cross out, and then we have the memory increase on the creation of the list by the list comprehension statement on exit. So yeah, we already had, yeah, just like, well, not magically, but because, yeah, we know what there's behind, but just by changing the kind of object that we are using to work on, we had a order of magnitude of using less memory by using, yeah, something more, well, something that has been developed for that, for being more efficient in memory usage. But as we just saw, the timing it didn't improve at all, just using exactly the same logic. But as I said, with NumPy, it's not just that I can create arrays with a given data type. We have a lot of methods, and even we have what's called slice indexes. We have an approach that allows me to do loop inside a NumPy array without writing a Python for loop. So if we replace the most internal loop that we had, the one that in which we are doing the cross out, if we replace it by the while that we had by using the slice indexing to iterate on the loop. So the logic here is this is the number. We are looping through this array, starting from the element n squared. In the second, if I don't put nothing, it will be up to the last element of my array in steps of n. So I'm using this approach, which is called slice indexing, to loop through a NumPy array and doing them equal to 0. But so yeah, here I didn't need to write a Python for loop to loop through the array. And then if we do that and we run this code, and we go to a massive increase in reduction in runtime, or a massive increase in efficiency. So if we now use again, so we on the same computer, we went from 10 seconds to 0.5. You can, as I said, now that you copied the directory in the examples directory, you have all these. It's named exactly as I'm showing on the slide. You have the code. So well, yeah, you can check now or later the fact of having this increase. Here I didn't mention, but in all the slides that you see the light, now that you have the PDF, the light blue color, you will see that it's a link. If you hover the mouse on top of it, so all the light blue text are links to different references. So if we want to take a look or understand why we had this massive gain in efficiency or reduction in runtime, if we run now the kernprof tool of the line profiler extension, yeah, we have to add the profile decorator to the function now to the function creating the NumPy array and then looping with the slice indexes. We see that most of the time of my code is spent here. But although now these statements are being hit by the Python virtual machine only 700 times. And I'm still spending most of the time, but it's most of the time that I spend in executing a binary library that I'm calling from here. So the loop itself, it's being done on a NumPy array by C code already, an originally C code that now it's a binary library that I can call from Python. So most of the time I spend it there, but what I'm running there is just pure C compiled code. And actually, that's a reason of having the massive gain that I'm running. Code that has been compiled. As you know, you have the source code of low-level languages like C or Fortran. You compile it. You are closer to, as I was saying, you have an array on a contiguous block of memory that you look through it. You are closer to how it's ideal for the hardware to execute those operations. You are also using sometimes vectorized instructions of the CPU that you have, so you can actually run the different operations additions at the same time. For a dot product, you can have a massive gain. By using for operations as dot products by using the vectorized operations of the CPU. I don't know if there's a detail. Damian, there was already a discussion on a session about the hardware and the in terms that you were giving one other years, right? But, about the how what does it mean vectorized instructions on CPUs and so on, or
no, it's part of the
okay. But the main thing to keep in mind is that actually I'm spending most of the time but executing code that it's binary from C or Fortran based source code originally. And actually you can try to implement the code on writing pure C or pure Fortran, and you will be hard to beat that. Because basically the code reduced to running already pure C or Fortran compiled. And here is a summary of what I said before. In the pure Python solution, we were spending most of the time here, but you see that they were statements executed by the Python virtual machine. Now we spend most of the time here, but from Python we are hitting that's just 700 times. It's actually each time that we enter one of the loop here. So it's each time this thing is true and we enter here, and then that's it. All the cross out is handled by moving through the array with the slice indexes method that provides a view on the NumPy array to operate on it. So now the following part is trying to see how we can build how this kind of how a module can be built, compiled and then executed from a Python code on our own. As a summary, yeah, well, as a summary of the profiling tools, yeah, maybe, yeah, the point of the, yeah, what we saw with the mprof tool is yeah, it's nice. It's with using the time stamping on the, so the mprof tool is the one that gives me the plot of the runtime, the memory used as a function of runtime. And we saw that it doesn't introduce a lot of overhead on the original runtime of the code. And then the time stamping and grouping blocks of code inside a timestamp, it can provide me yeah, as an easy approach to have a view of what's going on of the code, where I'm spending yeah, well, using the time stamping in a smart way. I can use it also as a kind of CPU profiling tool at the same time. And yeah, just a part of SnakeBees, there's another tool that allows to visualize the dumps of the cProfile tool. cProfile also doesn't produce a lot of overhead. This is the one. It's not blind profiler. It's the one that looks at the full code, and yeah, and dumps how much time is spent on each function. So yeah, you have links or references there to keep digging into those tools. And yeah, so now before going into how into the examples on how can we create our own module based on compiled code. Yeah, well, here there's a mention of different different Python extensions that provide me already, that are focused on tackling different kind of problems, but numerical problems. So the idea when I'm starting to work on my problem is to see to not rewrite algorithms that are already provided by but existing extensions that are open and free to use, actively developed. The idea is that's the main, that's a nice thing about Python, that the ecosystem is huge, and for a lot of different domains and problems, there are a lot of extension provided. And the idea is to be based on those, and then eventually there can be contributions done to those. And on the topic of doing the interface of Numpy, is an interface for Python to use compiled code. So there are actually two main ways to do this, is to actually write my if I have some kind of problem I'm working on an algorithm I have to implement that it's not available, to just simply use it from an existing extension. I can write Python, a kind of Python-like code. Is Cython the main language used for that. This is a mixture in between C and Python. So it looks most like Python, but it has some kind of C logic. So it's to write on something like that, like Cython is the main standard. Or if I have an existing library in C or Fortran that it's doing that kind of computation, I can just create a wrapper to that existing library. I can compile that library and create a wrapper, and I don't have to write a Fortran library in Cython or a C library in Cython. We have wrappers to do that. That's for having an interface from Python to compile code. Then a part of that, there's another approach which is based on use what is called just-in-time compilers. What I just mentioned before is it can be called, or is called sometimes, ahead of time compiler. So actually you have your Python code or C code or Fortran code, you compile it, and then you access it from an extension that you import on your Python code. But yeah, that requires to write in advance your algorithm in C, Fortran, or Python, compile it, and creating the module, the interface to access it. But then there's this approach. Mainly Numba is really focused on or being thought. It's actively developed by the people who develops Anaconda. So it's really focused on being a help to get more efficient Python code. So it will just, so you have just your pure Python code, and then by using this tool, it will compile that. So it will actually compile Python code to some binary and then execute the binary, but it will do that on the fly. And Numba is kind of it's the one it's in here is the most maybe interesting to explore. There are actually, we are starting to see that there are many projects that are starting to be based on it. And in order to, for instance, for Numba, if I have my original pure Python code, so here is really the initial, even with the bad definition of the not optimal creation of the sieve list and the loop and the pure Python loop on the Python list. So I have the less efficient thing that we saw on the beginning, and in order to execute that with Numba, the only thing that we have to do is import the JIT method from Numba, and we add the @JIT decorator to a function that we want Numba to do that. It will on the fly compile this, that it's pure Python code, to a binary thing and execute the binary. And if we do that, we get just without there's examples compiling Numba. Yeah, you see, just by doing that, the code was executed in 1.5 seconds from the if this was just to compare on the same machine, because so this is as I said, in the profiling folder, there's the zip01.py is the initial. So here we are on the same. It's just exactly the same as I ran. You see, I'm doing a diff of this one on the Numba folder, and my original first. The only thing that I'm doing, as I said, is an import Numba. I add the JIT decorator, and and like almost magically, I reduce like 10 times the execution. So it's it's a bit impressive. But then, of course, if I did the NumPy, if I run that against the NumPy, I will get nothing against the implementation with the NumPy array and the loop using slice indexing. I will see no difference at all. It's not the thing that something, not efficient at all. I will have a great gain, but the impact, of course, it will be less. The better is or the most I'm using already external extensions. I will have a less impact of using something like that. But it's something to keep in mind and to explore. As I said, it's been very actively developed. So it's something to explore all that it can provide. I didn't show. PyPy is. We don't have it on the clusters. The thing is that PyPy. The main thing with PyPy is kind of the same as NumPy. I don't modify the code at all. I execute it with the tool that PyPy provides, and it will also compile it and then run it. But the thing is that it particularly is not compatible at all with NumPy code. And then if here, instead of the Python list, I have a NumPy array, as we had in the second implementation. For NumPy, it's fine. It will run it. It's able to work with the NumPy arrays. But with PyPy, if I have a NumPy array, it will crash. It won't work. And for sure, this was just an example to illustrate. We will always, if we are going to operate to do computations, we will always start our code with the NumPy arrays. We will never use vectors represented by Python lists. And then PyPy, in that sense, it will be very fast leap out of any kind of scientific development. But NumPy, on the contrary, is fully compatible with NumPy, and it's actually developed to integrate with it. And then, just something that, to keep in mind, to explore. But then, let's go to how we actually create a compiled. How we have, if we have a given function on our code and we want to create a module which provides an interface to a compiled library. So if we want to write my primes up to function in Cython at the very basic on the most let's say the less intrusive modification of the pure Python code in order to write it on Cython. What we have to do already is define. We need on Cython. We need already to define data types. So here we define that the data type of the variable entering here will be an integer, and then these internal work variables of the function, they will be also integers. And just, in principle, that's the only modification I did to the pure Python code. We added some statements which are part of Cython that allows to that are required by Cython, and then we can compile this. We will see on the next slide how we compile it, and when we compile it, we obtain a binary that can be imported as a module on a Python code. So then all this is compiled and packaged on a binary that we can from a pure Python code import my primes up to library and ask, okay, give me all the primes up to 30 million, but my Python code then is being reduced to this. the function doing everything, it's been compiled. And yeah, so in order to compile Cython code, so this part of code that I showed before, so this, if I call it, if I save that on a file with a PyX extension, is the extension for Cython code, then we write some kind of, oh yeah, you probably saw many Python extensions that you can, yeah, that are publicly available, that sometimes you have to download it and compile it on your own. You maybe saw this setup.py file coming with all the Python and Cython code. You need this at the minimum, yeah, this kind of file that it's a helper, it's a kind of makefile equivalent for Cython. You will this then to write this setup.py. This is the code that we saw on the previous slide. And then you tell that you want to build an extension from it. And yeah, by default, it will create a module that it will be called like the file name of the Cython code. But so you have two files on your folder. This with the code I showed before, this that it's called the setup.py, and then you execute this like that, and you will obtain actually a binary file on that folder. And then zip01.py is just the code that imports ziplib, that imports the primes up to function from ziplib. And yeah, so by doing that kind of thing on this machine that we were on the 10 seconds, we are going to 2 seconds by running. I don't know if in case it was not totally clear. I would just, we have the examples here. So for Cython, we have, as I say, the ziplib. The PyX is the primes up to written in Cython, which, as I said, what we did is the minimum is just given data type, provide data types to all the variables involved. zip01.py is just importing the primes up to function from ziplib, but then I have to create it. Setup.py is what I say, the helper that allows me to build the code. And we execute it, and we see that, yeah, we have here GCC involved. So we get this stuff created. This is the real binary being created. But now, yeah, by having this file on the same folder as zip01.py, I can import then stuff from this library. And yeah, if we I didn't put time. And yeah, well, in this case, yeah, it's we are running this as in 0.6 seconds. So yeah, here you can see a little bit how you actually create. How do you write code that you compile and then you import the methods provided by that compiled code, but then actually, yeah, you see now your Python code is mainly just a single line in this simple example that we took. But yeah, well, then you get a you get something that is way more efficient than running your pure Python code. So this is Cython is the most. If you are going to write, if you are working on Python and you are going to write from scratch, probably you have some kind of, as we had here, some kind of initial mix of NumPy and pure Python, and then you want to create a precompiled, to create a module out of it. Then you can get your mix of pure Python and NumPy, for instance, and actually package it as a port that to Cython and compile it, to have an even, you might, well, depending on how is structured your algorithm, you can take advantage of porting a part of your Python code to Cython and compiling it and treating it as a module. Then I think what this should have been afterwards. There was another. There's another. So Cython is, it works this way, as we just saw. So you have to write in a kind of new language, a mix of Python and C, and then you compile it. There was another project that I was mentioning in the previous years, Python, that it provides also the possibility to do something similar to Cython, but by modifying even less the original Python code. But the project is not being actively developed. This is just a leftover, and it doesn't work for the way it's not being actively developed. Each time that there's a new Python release, it's broken. So Cython is almost the standard for writing. If you are starting from Python code to port that to something that you want to compile, Cython is still the big project that you will find planned. A lot of documentation, help, forums, and so on. There was, it exists Python, but it's more like a niche project. The thing, we still didn't, you didn't have still the sessions about parallel programming, in which you are going to talk about so how to exploit the fact that you have a lot of processors on any right now any laptop you have already 4 cores, and on the machines on the clusters you have between 30 and 60 CPU cores per machine. So in the if you are going to, if somehow your problem can exploit the fact of having multiple cores, and OpenMP is one of the main approaches. There will be the session like in 1 month in December about OpenMP and MPI. But so about OpenMP, just keep in mind that Cython provides an approach to produce OpenMP like code. Cython. When I at the beginning I said that if you want to do an interface for Python to a binary library, it might be that you have to write the library from scratch. Then it might be that Cython is the natural way to do it, but it might be that there's already a library for the part of your that required on your code. A library already available, but like in C or Fortran. Then you can just create what is called a wrapper to that library. And Cythons allows to do that for pure C code. And then provide you an approach to execute, to create a module that you can execute from Python. There's I will show the example that I mentioned here on the slide. So in the folder that you copied, in compiling this, there's this folder, and here we have the library, and here is just a function. It's a small library here, a single function. But you see, this is really pure C code. It's a function in which the input is n, and it provides me the nth Fibonacci number. So of the Fibonacci series, I give n. So if n is 10, it would give me the 10th Fibonacci number. So it's just doing the typical loop to get n the nth Fibonacci number given an integer. But you see, it's a pure C code. Let's say that you want to write a Python code that would, you see, the Python code will be something like that. From a module we import a function, and then we actually we execute a little bit like we saw with the primes up to before. The main difference is that instead of the primes up to, which was written in Cython, here cfib is a pure C code. So that's in the case that you already, that there's already available C code or a C library. And so here I have a make-file, and we have a setup.py. So the setup.py here, it will instruct how we use Cython to build a wrapper for this library. So we have actually the cfib.c, which is a pure C code, and then a Cython code which is the wrapper to that library. And the Cython code is very minimal. It's just to define how we interact with this pure C code. But with this Cython wrapper, we can then create, well, here it was already, this was already present, but if it's not, it will be actually then the C code and the wrapper compiled to provide the graph cfib module that then I can import my test.py code, and then I'm using a wrapper is that it's just that it's an interface to pure C, a library, a binary library. In this case, the library is written in C, but there's another tool that in case we have already, like Fortran code doing part of the computation that I need on my problem. And there's we provided with Numpy. So when you install Numpy anywhere, there's an extra tool provided with the Numpy project. It's called f2py, or Fortran to Python, and it also allows which allows to easily create a wrapper of Fortran code. So if I have yeah, here I put more details. So in the same folder where you have all the examples, there's an F2Py folder that you will have a hello.f90, which is like that. It says a Fortran subroutine, just but it's just pure Fortran code, and then with F2Py we can create a hello module by compiling this pure Fortran code. I will get create also a binary there on the folder, which and if that binary is right next to a Python code, as simple like that, then I can import the module, and then I can execute a function provided by that code. So from this way, when I run this, I'm actually executing this already compiled Fortran code. So it's the kind of thing that are done. So even the development of Numpy itself is mainly C code, pure C, with Cython wrappers to that. So it's more the approach of that we saw with the Fibonacci thing. And yeah, so as already gave some kind of conclusions, but as a summary, if you have your Python code and you have to start porting something of it to something to be compiled, then it might be that Cython is, but it depends on what other background you have with C or Fortran. You might be comfortable to just say, okay, I write it purely in Fortran or purely in C, and then I use Cython just as a wrapper to pure C code. Or you might decide to write actually Cython code, which is this mixture of Python and C. But in both cases, either using Cython as a wrapper to pure C or Cython to compile Cython code, you get a binary library that you can call from your Python code. And then, PyPy, it's not really targeted to the numerical to code or linked to doing huge numerical computations. So it's mentioned just because it's still a big project, but it's not compatible at all with the numerical ecosystem, let's say. And then Numba is something that we are seeing that more and more projects are being Numba based actually. So it's something to keep an eye to explore. We saw that sometimes with almost not a lot of effort, you can already get some notable speed up. And Python, as I mentioned before, is in a very experimental. It's something still very experimental, and it doesn't look like it will gain traction. Related, you still didn't have the as I mentioned before with OpenMP, the parallel processing, but the session dedicated to parallel programming. So that means how to exploit the fact that I have a lot of cores either on a single machine or a lot of cores on different machines. You will see it on there will be in 1 month the session about OpenMP, which allows to exploit the fact of having multiple cores on a single machine. And then MPI, then you have the session about MPI, which is a programming well, MPI is a library providing a programming kind of programming API to exploit the fact that to provide an approach to use different cores that are on different physical machines. So for MPI there's a big very quite actively developed project, MPI for Pi, that provides well, actually it's a bit like we just saw. It's based on providing an interface or wrappers to the MPI library developed in C, if I'm not wrong, or C++. But yeah, it provides an approach to use MPI from Python. And then linked with OpenMP, there's now, since 1 or 2 years, there's some a project that looks quite interesting, which provides an approach of having OpenMP-like code inside Python. Well, the thing that we cannot go through what's OpenMP or MPI right now in 2 minutes. But remember, after if you are interested in parallel programming and you will follow that, and you are interested in parallel programming in Python, after the MPI, of course, follow the MPI and OpenMP sessions in 1 month, and then you can explore these tools for either using MPI or OpenMP from Python. And then on a different kind of approach, you have these two, well, the multiprocessing model, which is part of the Python standard library. So it's something that can allow you to span different threads on different cores, and then split a bit the workflow of your code to create different threads that will do different operations at the same time. So then you exploit the fact of having multiple cores. But just the only thing to remark is that with this kind of approach, it can be really trivial if you have a single a single array or a couple of arrays. It can be non-trivial how to share the information that you have on array that you created, and you have to do operations on it. It can be non-trivial from different threads of your pool of threads to operate on that single array. That's something that is totally natural in OpenMP. And then there's this shoplin module, but it's a bit kind of the multiprocessing one is more. It's more designed like well, you already got the Slurm formation. You know that to run jobs on the cluster, you have to submit scripts to a job scheduler, and then if there are no resources available, it stays in the queue, and then it will run at some point. Joblib, it follows a bit of that kind of logic. I mean, you have your Python code, and then you will take one part of your code and you tell that to be executed on one core, and then another part, but it's kind of part that are very way too independent one from the other. So that kind of thing is called sometimes embarrassing plus. I cannot pronounce it. This kind of problem, embarrassingly parallel kind of problems. So actually, what you can tackle with Joblib, you can already tackle even with the job scheduler with Slurm. I mean, maybe you have a Python code and you need to run that for 2 different inputs, like 2 different values of temperature, but then it's really completely independent, one run from the other. So instead, you can just do that with you can then submit a single job. So submit what is called an array of jobs with Slurm. It's just a feature of Zoom. And so you submit 2 times, well, depending on what what you need to compute, but you submit a single job that it will launch a set of sub jobs that each one is fully independent from the other. They just start like with reading the input data from different files. So yeah, I would say at least with the kind of the kind of so the main the 2 main approaches in HPC to exploit or the 2 traditional approaches to exploit the fact of having multiple cores are OpenMP and MPI. That's talking about CPUs. Then yeah, for GPUs, then you have but it's a completely different world. But exploiting multiple CPU cores is OpenMP and MPI. So you have these options to create a parallel code with Python by using those approaches. And then, yeah, well, then you can see on the README, there's the suggestion to experiment some of the things we already did. It is like doing creating the wrapper for the Fibonacci for the using Cython to create a wrapper to the C function to compute the Fibonacci number. So you have all the examples and code snippets in the examples folder, and you can at your own pace then take a look at those and then get familiar a little bit on how to compile your own code. Yeah, this is the final slide, like with some recommendations to keep. So writing efficient code in any language is a big topic. There's so here, there's the way in which this full presentation was structured is strongly based on how the topic is presented on this book. So it's a really nice book to if you really want to go deep into the different topics that we talk and even more. Yeah, this is a really good reference. Here is a GitHub that has some nice set of examples, and then there's also this is very interesting. This is one of these online courses developed by the one that you can follow on your own at your own pace, which was sponsored by Place. And I don't know why on full screen I don't have the mouse. So yeah, from the slide you have the link to this. So it's one of these sites of online courses. But this one, which was sponsored by Praise, actually you can, and it's exactly the topics that we've been. So Python for high performance computing, or how to do. So the topics that you see, you have the performance analysis is main based on discussing the profiling tools that we saw at the beginning. Then a kind of more dedicated introduction to Numpy, using compile code with Python. So also going through a bit that use or write what we saw using Cython or scipy or I don't think they talk about Numpy, but Cython for sure, or interfacing Python. So we see what we saw, like the Fibonacci example, how we create wrappers to libraries that are already existing in C or Fortran. And then they have some kind of introduction to MPI. They don't talk a lot of OpenMP, but they have some small introduction to an MPI, and then how to do parallel programming with MPI for Pi. But yeah, so as it's mentioned here, it's something that like 4 hours per week, it would take you 4 weeks, but you can follow it on your own. And this one, you can register on the website, and you can do it fully for free. The only thing is that, you see that from the moment that you create an account and you click join, it's available for 1 month. So if you're going to, but if you want to go keep exploring this, it's well structured and with examples and so on. It's a nice thing to do. Just remember that when you join, do it when you have a couple of weeks with some time to spend on it, because then it will be blocked. But it's a nice thing to. Well, I don't. So that was it for this session. Do you have questions or? Well, I think we can put. But we are done for today. So thank you.